Welcome back. In this video, we will be covering practice questions about the Wittig reaction. Now, some people do find the Wittig reaction challenging because there's a few variations. There's 4 of them in this class that you have to worry about. And there's different types of ylids going on, different types of carbonyls. And so some people do find it a little bit confusing, and naturally so. In particular for this video, I'm going to be focusing on these types of ylids, the stabilized ylids, because a lot of people find it troubling with how much stuff there is going on with those ylids, and they find it a little bit confusing compared to the top two. So the first question I'm going to do is going to be about one of those stabilized ylids. So let's say we have a compound. That looks like this. We have an aldehyde, and we react it with this. So what do I see? I see a carbon with a negative, and it's connected to a phosphorus. In my head, that should ring a little bell that tells me it's a Wittig reaction. Even though there looks like a lot going on there, the important part to recognize it's a Wittig reaction is really just right there. And they could have just as easily, again, written it like this, where that's resonating up, and we get this. Okay, so either version works. Now, which one is this? Let's look at my ylid. First thing I notice on the phosphorus, there's no phenyl groups, those pH3 groups. So I know it's not one of the first two that we learned. It's not one of these. It doesn't have this group on there. What else is different? If we, again, the little trick I showed in one of the previous videos, it was cut right here. The part with the negative and onward, so this way, is the group that we're actually adding on to our compound. If we look, that negative is right next to that double bonded O. What kind of a group is that? Well, if you don't know off the top of your head, don't worry about that. If you know resonance, you can always figure this stuff out. That negative can drop down here, pushing this bond up. In other words, that group is taking the negative further from the phosphorus to create this compound. So by taking electrons, it's an electron withdrawing group. So that's why this part over here is different. It's not that PPH3. It's actually that other version we have for the bottom two reactions, this thing. And so we have one of these ylids with that other group on the phosphorus, and we have an electron withdrawing group. Now in this case, between these bottom two, the bottom one has carbons with 3 fluorines on them. If we look back, we don't have that there. So this is actually the HWE modification Wittig reaction, which generates an E isomer. Now that I know that, I can do the question. So how do we do this? We number everything from the negative onward. You can number the oxygens in that ET group if you want, but you don't have to, whatever helps you guys. And we can number this. Oh, let's do the different numbers. So I'm going to redraw that big chain. When in doubt, always number. helps prevent losing a carbon randomly. Oh, and I missed the number here. 6, 7. Now, that oxygen on carbon 7, so the carbon 7 used to be double bonded, so it should still be double bonded. Now, from the fact that we know it's the HWE modification, we know it's an E isomer. So whatever is coming out of that double bonded carbon should be in the opposite direction from the big chain, which means in that direction, not in that direction, because they would be both going there. Now, carbon 7 connects to the carbon with that negative. So that's carbon 1. And now it looks complicated to draw, and this is where numbering helps you. You know where what is connected to each number. 1 is connected to 2, and I know it should be written this way. 2 has a double bonded O on it, and it's got an oxygen with an ethyl on it. And that is my product of the HWE modification Wittig reaction. I hope that problem made sense for you guys. And if you have any questions, feel free to reach out or leave a comment. Now, let's go to a different practice problem. So, in this new example, which you can pause it and write it down if you want to give it a shot beforehand. We're going to look at something else about the Wittig reaction. So let's say they gave us something that looks a little bit on the stranger side. So let's say they gave me this question. So let's say they give me this, and they ask me what my product is. So let's take this step by step. So first off, what kind of Wittig are we doing here? So we have a pH3P group. If we go back, that's one of the top two. Okay, and I know it doesn't have an electron withdrawing group here, further confirms the fact that it's one of these unstabilized Illid reactions. Now, between these two, the difference is this extra base modification, the presence of PHLI. We don't have that here. So that tells me it's the top reaction. So whatever Wittig reaction I'm doing, I'm getting the Z isomer in this case. Okay, so we can make a note of that. We're getting the Z isomer. Now, let's try to figure out how to do this. So here's the tricky part. Wittig works on carbonyls, double bonded O compounds. I don't have that here. What do I have here instead? Hopefully you guys recognize this functional group. You have a carbon that is connected to two oxygens. One of them is an OH, the other is an oxygen connected to a carbon, which we can call an R group. So another way of really kind of writing this is that. It's like this. And the carbon itself is connected to two other groups, doesn't matter. But that functional group should be something you guys are familiar with, and it's called a hemiacetal. So we know this is a hemiacetal. What does that do for us? Well, there was one important thing about a hemiacetal. Hemiacetals are in equilibrium with the carbonyl version. So what does that mean? We can reverse the hemiacetal to become the carbonyl. If you're unfamiliar with the mechanism, I'll still show it, and then I'll show you the shortcut way. But it's good to know the mechanism in case they test you on it. So we have some H+. The oxygen that has the R group, and in this case I'm using R as a carbon, so not the OH compound, not the OH part. this oxygen grabs that H and protonates itself. Next thing that happens after protonation, OH drops a lone pair down to form a double bond. This bond breaks onto the O. So my OH is double bonded now. Still has the H though, and it's going to have a plus. And this is now an OH. All that happens now is the H over here drops off. And we have our neutral carbonyl. Now I see my carbonyl. Now I can do my Wittig reaction. So now I can do the Wittig reaction. So how does it work? We number this. I'm going to redraw this, and remember the Wittig only affects ketones and aldehydes, so that OH is going to be perfectly safe. Four used to be double bonded, so it'll still be double bonded. It's going to connect to the carbon double bonded here, so 1. And it's got to be the Z isomer. Z means the two chains are in the same direction. So either this way I got to draw it, or this way. This is coming down in that arrow. So this chain here is the one I want to pick. The other one is going to be in the opposite direction. So 1 is connected to 2, and 2 is connected to 3. So that's a common question that a lot of people have a little bit of trouble with because there's no carbonyl here, and it can be a little confusing when there's no carbonyl there. So the thing to keep in mind is hemiacetals are in equilibrium with the carbonyl version. And so once you spot it's a hemiacetal and you know exactly the type of Wittig reaction you're going to be doing, then hopefully this question will be much easier for you guys. So I hope going through these two problems was helpful, and I will see you guys in the next video.